Hello, and welcome to the Introduction to Planes in Space. In various applications of science and engineering, we often encounter three-dimensional surfaces which need to be quantified precisely. The simplest among such surfaces are planes. In this video, we hope to give you an understanding on how to represent these planes in the context of the three-dimensional rectangular coordinate systems. Like with geometry and lines, vectors provide a fantastic and efficient tool for us to quantify these objects very precisely. Suppose that we need to construct an equation that represents a plane L in space. To do so, we need to pick an arbitrary point on the plane, say the point P, having coordinate x0, y0, z0, which can also be represented as the position vector OP having components x0, y0, and z0, where O is the origins of the coordinate system. Previously, when we represent a line, a vector was used to describe the direction of the line. However, since a plane expands in a number of different directions, we use a vector called a normal vector to denote the direction perpendicular to the plane. To represent an arbitrary point within this plane, say the point Q, which has the general coordinates x, y, z, we observe that since vector PQ lies on the plane, it must be orthogonal to the normal vector n, and hence, through the dot product, we can write this relationship as PQ dot n equal to 0, which is a scalar equation. Or algebraically, we can write the same equation in terms of the vector's component as shown. With this equation, we can check if a point is in the plane if its coordinates satisfy the scalar equation. Previously, we have learned how to find the distance of a point to a line. We can also, through means of vector operations, find the distance between an arbitrary point and an arbitrary plane. Suppose that we need to find the distance between a point A and the plane L, whose normal vector is n. To do so, we need to pick an arbitrary point B on the plane. The distance we're looking for is simply the magnitude of the projection of the vector BA along the direction of the normal vector n as illustrated. In summary, we have learned that in order to quantify a plane in space, we need a reference point on the plane and also a normal vector to the same plane. Also, we have learned a simple technique to find the distance between a point and a plane. In class, we will be dealing with other relationships between points, lines, and planes, such as finding distance between a line and a plane and finding the line intersection of two non-parallel planes.